Okay. Hello, everyone. Thank you for joining the seminar, first by Lena Roald. So I would like to give a small presentation of Lena. So I'm sure that many of you know Lena. And we have 18 people now online. Thanks for joining. So Lena and Josh, both of them, they were examiners of a PhD defense yesterday. So they kindly also agreed to stay with us also today and give a seminar on their recent work. Thanks a lot for joining. First, Lena will talk for half an hour, and then we will have a Q&A for half an hour, and then at 11 o'clock, it will be Josh continuing the seminar. So about Lena, Lena got her PhD in electrical engineering at ETH Zurich with Joran Anderson. If you don't know, he's a legend. And yeah, then Lena started a postdoc at Los Alamos while securing her position as assistant professor at University of Wisconsin-Madison. That's so amazing. So after being a while, a couple of years, I guess, at Los Alamos, Lena joined University of Wisconsin in Madison, first as an assistant professor and recently promoted to associate professor. Lena, yeah, did a lot of contributions to our field. I know her in the first time with pragmatical chance constraint modeling for optimal power flow, but after that, I mean, Lena did a lot of things. Recently, she's working on resiliency and risk management and wildfire stuff, especially for California. But yeah, the main maybe interest of Lena is uncertainty modeling, risk management for energy systems, not just power systems, but also gas, recently hydrogen, and others. So Lena, thank you so much for joining us, and we are looking forward to hear your talk.
Yeah, thanks, Jalal. It was a very nice introduction, and it's been really nice to be here. I mean, Enrica is not here today, of course, but it was a really nice event yesterday, and I learned a lot from reading Enrica's thesis and also being there for the defense. So it was very close to what's going on here. So Jalal, every time I get an email from Jalal, I get very excited because I always know there's something interesting that will happen next. Okay, so what I was gonna talk about here today is something that we've been working on, which is maybe slightly different than some of the other things some of you maybe heard me talk about before. And specifically, I wanted to pose this question of how consumers most effectively can reduce the carbon footprint of their electricity consumption. And this is a question that I spent quite a lot of time thinking about, and that I'm, trying to develop further. So this is still work that is very much kind of ongoing and happening as we speak. But yeah, let me kind of give you some thoughts on this. And you will see also here that there's a flavor strongly of data centers and computers and computing in this, in kind of the case studies. But I do think that sort of the question of how we all can act sort of independently to try to reduce the carbon footprint of our electricity consumption is something that actually is interesting to many people in many different settings. Okay, so this is just to kind of start out here to acknowledge my collaborators. This is Julian Lindbergh, who's currently a student in Madison, now a postdoc at UT Austin. And my colleague Barney Lasud, who are both, have been very essential for this work. So we've written a few publications together, which are kind of the basis of the technical part of this talk. And also I want to acknowledge support by the National Science Foundation in the US, as well as VMware, who has very generously supported a lot of this work. Okay, so when we think about carbon footprint of electricity consumptions, I mean, what we know is that when we generate electricity, that generally tends to produce carbon emissions. Particularly, historically, of course, we've had power plants that burn coal, gas, and so on in order to generate the electricity. Now, as we have more and more renewable energy, we also see that there is a stronger time component and location component to that carbon footprint. Specifically, if the sun is shining or the wind is blowing, many times it's possible to get close to zero carbon power. And so because we have this time and location varying carbon emissions, people have then started asking, how can we understand this in order to use electricity when the carbon emissions are low? And so there are many different types of electricity consumers. There are individuals, companies, organizations, and many of them are interested in this question of how can we reduce our carbon emissions. It's really like we are dealing to mitigate our impact. Maybe people want to do something voluntarily to really try to be green, to mitigate climate change, or it can be companies, for example, that are increasingly being something to track carbon emissions and so on. And so if you think about, there are many things you can do to try to reduce your carbon footprint, but if you think about this sort of as a real-time question, given that I have a certain set of assets that I can use, how can I actually manage my electricity consumption in real time to reduce the carbon emissions? And I think intuitively here, the idea is that we somehow want to align our consumption with the availability of renewable energy generation. And I think that in our field, power systems, there has been very much a focus on sort of this lens of let's help the grid. If we make the grid work better, we are going to, absorb more renewable energy, and in that way we can help facilitate transition to more renewable energy. And I think this is a very, very important component of this. Things like the demand response, market participation, and so on, very important piece of this. However, there is also a very kind of consumer-focused lens to this, where, when you talk to people like a data center company, they might say, actually, it feels like it's very sort of roundabout way of reducing my emissions to participate in demand response or in the market, because I have no way of tracking what my impact was. And so it would be much more interesting to me if you give me a signal that I can follow, and then that will help me understand when the grid is low carbon, and that is when I'm to use electricity. And so I put a picture of an iPhone up here. That is just because in the US, currently, if you have an iPhone, there is a button.
Nice done.
Yeah, okay. There's a button that says clean energy charging. It is on by default. And what happens when this is on is that Apple somehow manages the charging of your phone to align with when there is green energy available. So Apple is not the only one who does that. Apple has some statements around that it combines grid emissions, weather information, and so on into one easy-to-follow signal. Samsung has something called SmartThings, which also leverages information about this to help people reduce their carbon footprint. And then when you talk to companies like Google, they also want to shift their data centers load, and they want to do it sort of in a way that helps absorb the renewable energy. So one of the really challenging questions then that arises is what signal to follow. So I will say that it's kind of very interesting, and I think very good that these capabilities are being developed, but it's not very easy to know what is going on under the hood here. And there is a lot of different ways in which you can think about this data, different providers, and there are many different metrics. So here I've just put up a few. The electricity maps, which is a Danish coming from DTU, right? I'm sure most of you must have seen these maps that show sort of the carbon content in different parts of the world. There's What Time, which is an American organization that also provides similar information. Singularity is a recent startup that also provides this kind of information. And then actually PJM in the US has also started providing real-time information about carbon emissions with the sort of note that you should not use it for load shifting, which I don't really know. So there's a lot of different data. There are different kinds of metrics that are being provided by those providers. And it's not so easy to understand which one is the best one necessarily. So that's one of the things that we set out to try and understand better. But before I go into our kind of quantitative sort of information about like our case studies and so on, I wanted to just give you a little bit of intuition. So if you look at the California energy mix, so this is June 10, 2021. And you can see here there are different types of generation that is going on in different colors. The most important one to understand here is that this green one here is renewable energy generation. As you can tell, it's mostly during the day, so it's driven primarily by solar generation. And from this information here, you can calculate the carbon emissions per unit of power. So this is the sort of essentially how much power is there in 1 megawatt hour in the California grid during this day. So if I ask you, if you were to use electricity in California on this day, when would you want to use it if you were to be low carbon, if you want to reduce carbon emissions? I think it intuitively makes sense that maybe you want to use it when the carbon emissions are low, right? So maybe during these hours of the late afternoon, when there is a lot of solar available and the carbon emissions per unit of power are low. And then if we do this, then this is akin of saying, like, if I calculate the average carbon emissions of the power in the grid, then let's use it when that is low. However, what is very interesting and important to know here is that these graphs that show the generation only paints part of the picture. In fact, the reason there was more renewable generation earlier in the day here has nothing to do with the fact that it wasn't there. It was curtailed because the grid wasn't able to absorb it. And so now you can see that on this day in particular, there was more than 3,000 megawatts of a renewable curtailment during parts of the day. And of course, if you are now able to somehow use that, instead of seeing it become curtailed, then you could essentially use zero carbon power. And so this is something that is better captured by this idea of marginal emissions. If I increase power consumption here, then maybe I can use the curtailed power that is here so that I can get access to zero carbon. And of course, this now leads to the situation where I'm not sure I painted this, but like essentially now it means I would want to use power during a different part of the day. So the decision making on these metrics can become quite different. And then of course the curtailment, I would argue, is really the big opportunity here. So as we are going towards more and more renewable energy, there is also an increasing amount of curtailed energy that is becoming available. Maybe we will figure out large-scale storage and everything, but definitely there is a transition period that we are going towards where we can be facing a situation where during certain parts of the year, during times of the day, there's going to be a really significant amount of curtailed renewable energy. And essentially here, and my point would just be that if you look at average carbon emissions of the grid, that only looks at the actually generated power. It doesn't look at the power that was not generated. So that is one important thing that it doesn't capture. So this is now from this last year, April 2023 in California. There were 702 gigawatt hours of energy curtailed in just that month. That's on average 23.4 gigawatt hours per day. And of course, it's not spread evenly throughout the month. And you can see that there are certain times of the day and in parts of this month where you were 8 gigawatts of power that would be curtailed in California because it couldn't be absorbed. And if you look at this, I made a slide 1 year ago on this, and then I said, oh, it's like 530 gigawatt hours. It's been increasing incredibly much over just the last few years, and it doesn't really. I mean, it hasn't been showing any sign of becoming lower. There's still solar that is being installed in California. Of course, we can also ask, why does curtailment happen? I mean, we are power systems people, so we understand that there are different components to this. I mean, sometimes simply there's just too much energy available. That is what is highlighted in blue here. But then there can also be times where there's too little transmission capacity to transport that power, and that is what is in green. And so, of course, it's important to know that it's not only about how much power is available, it's also where it is available. And that leads to the question then that we also have to consider the locational component of these marginal emissions, in particularly when there's too little transmission capacity. And so we can think about these marginal carbon emissions as the change in carbon emissions over a change in electricity use. And we know that those can vary depending on location. In particular, sort of the intuition behind that is that in electric grids, we're used to the locational marginal pricing, where the numerator here is not the carbon emissions, but the cost, the changing cost. And so these marginal carbon emissions are very closely tied to the idea of marginal prices and probably also locational marginal prices. So the LMP looks at generation cost over the change in generation cost over the change in electricity use. And so just as here, this is just a map from California again. This is from November. And you can see that in different parts of California, the price is different, the LMP is different. And that has to do with the fact that there are different marginal generators in different parts of California. And because there are different marginal generators, it also means that we have different marginal emissions. So you can kind of see how those are very closely tied together. Okay, so yeah, so just coming back to this, like which signal should we use? Average carbon emissions, maybe locational marginal emissions would be good. So there are some pros and cons of both of those. Average carbon emissions are currently quite widely used, I would say. They're also quite easily accessible. Most operators of power grids actually released information about the generation fleet that is used or the type of generators that produce power. It's also kind of easy to apply for accounting purposes because you can just say I consume this much, and this is how much the carbon emissions that translates into. But it is not necessarily the best metric for guiding shifting decisions, right? When am I going to, like, if I want to try to change my load in order to reduce carbon emissions. That is, this locational marginal emissions has the benefit of being able to capture the presence of curtailment and transmission congestion, so it does really provide better incentive for real-time shifting. It is quite limited in availability. Some of these services or these data providers that I mentioned before, they do provide marginal emissions data. I will say, and I think they will also acknowledge that this data is a little wobbly. It is hard to know if it's actually, there's little ground truth data, so it's hard to say how good is that data. So currently, I would say that there is some limited availability for this. PJM is, as I mentioned, providing this for their area in the US. And there are also other questions, such as like, how do you actually align these locational marginal emissions to an accounting scheme that I think are sort of more fundamental questions that are really hard to answer. Okay, so I don't know, I probably already talked a whole lot, but I wanted to give an example of, you know, how you can use these different kind of metrics and what comes out of that. And so I want to just switch gears and talk a little bit about data centers. So this is a picture of a data center. And I think there are some very important trends in computing that are important to be aware of. So in the decade from 2010 to 2020, there was a huge increase in the computing needs of the world, with very modest increases in power use. And how that was possible is because it was really, we made incredible gains in efficiency of computing. A lot of it was funneled into these hyperscale data centers that have more efficient hardware and more efficient cooling. But currently, we are really at the point where the kind of the efficiency gains from using less cooling for the amount of computing that we're using are more or less exhausted. Like very much of the power that goes into a data center today really goes directly into the servers. And so today it is really, you're really kind of at the stage where, of course, I mean, hardware continues to improve, software continues to improve, but computing as we're moving forward can be expected to translate, like increased computing needs translate much more directly into increased electricity use. Because those efficiency gains are largely exhausted. And of course, there's a lot of new computing applications. I mentioned here Bitcoin mining, training of ML models, increases in internet and computing use. I should, of course, have put ChatGPT on here. Like all of these kind of things that we are doing, it does require, like, you know, even just Google search. Like when you're searching Google is improving their algorithm. They need more energy in order to do better things with that. And so there's just like, we are kind of used to this being fairly unlimited, but that might change. And so this is just an example from Dominion Energy in Virginia. And so just to kind of give you, I just took this here to give you a sense of like how big this is. So this is some little part of Virginia up here, where a very large portion of the world's internet traffic goes through. And you can say, I think they have several gigawatts already there, but they have as they are looking at new projects, they are talking about close to 6 gigawatts contracts where data centers have contracted with Dominion to build new data centers in this area. There's another 2 gigawatts which are looking on kind of doing substation building, like looking into building new substation connections. And a whole lot of more projects that are interested but kind of less developed and probably will not all be realized just because the grid is not able to support it. When you talk to people in the US about this, they will tell you that actually Virginia, the grid is so overloaded now that they are looking for the next locations to start building this data center. Apparently Chicago is another kind of place that is coming up for this. Okay, so this is just to tell you like data centers is a huge thing. So then, and then we hear from all these tech companies that they are very interested in being green. They want to buy renewable energy. They want to try to track carbon emissions. So you hear this from Google, you hear this from AWS, and so on. And essentially, if they are really serious about this, how should they actually interact with the grid to reduce emissions? One very cool thing about data centers is that they are able to shift load geographically. So many computing workloads can be processed at different locations. So you can sort of choose to process a computing job maybe in Chicago, in Virginia, or in California. And of course, that means that you can shift also your energy use around. There are many limitations, latency requirements, availability of the data that you need to do the computing job, hardware availability, and so on. But kind of assuming that there is some flexibility here, and there typically is because there is redundancy in the data center infrastructure for security purposes, then how should the question that you can ask, and which we have been also asked by VMware, which is why we were working with them, is how do you do load balancing of computing jobs between data centers in order to reduce carbon emissions? So there is a significant amount of work on data centers, demand response, geographical load shifting, and so on. But most of these studies consider some kind of integration either with the market or a direct collaboration with AISO. Or if they are assuming that the data center is working on its own, they have not really been looking at this question of what signal is the right one to use in order to, they have kind of a limited visibility of the grid. So since I'm now saying that other people have looked at having the data center directly participating in the market, you can ask, like, why shouldn't they? They are really big actors. And one answer to that is that the objectives don't necessarily align. So electricity markets are really run to minimize the cost of electricity, which is great in general. But maybe if a data center really wants to try and see if they can reduce their carbon emissions, that is a different objective than trying to minimize cost. Of course, we can have carbon taxes, everything like that, that can improve this, and probably is a better solution overall. But absent of like sort of big market reform and introduction of new carbon taxes, how maybe these objectives are not directly aligned. And then, of course, the data centers are very they can be quite secretive about how they do things. It's a very competitive market. So they want to maintain their privacy, and that can make it hard to include them in the market clearing. So they want to kind of keep they want to be able to manage their operations on their own. And so then, what we were kind of wanting to understand is, can data centers maybe even achieve larger emissions if they are trying to emissions reductions if they are trying to manage their load independent of the market. So that brings me to kind of what I really wanted to talk about. So all of this, it's introduction, but I hope it's still interesting because there's a lot of things that there's a lot of thought that goes into that. So let me give you some actual quantitative stuff here. So let's think about data center shifting as this. We have an electric grid where we have generation and transmission constraints here in black. And then we have a network of data centers that are essentially overlaid on that electricity network in red. And of course, there are computing and communication constraints, shifting capacity, shifting costs that determine how you are able to shift computing nodes between them. And then at every node, we can have information such as the locational marginal price, the locational marginal carbon emissions, and possibly also maximum computing capacity information about each of the things. So then our approach to thinking about this has been to say, okay, we think about the electric system operator solving the DCOPF to clear the market, is then taking that solution and compute the locational marginal carbon emissions per node. And you can do this using LP sensitivity analysis. And then given that information about locational marginal prices, the data centers determine their optimal shifting, determine the optimal load shifts based on their these marginal emissions. And we can, of course, here also consider other types of, instead of locational marginal carbon emissions, you could also other signals. So essentially, a little bit more detail, the cost minimization problem that is happening by the system operator is essentially a standard DCOPF here. And then we calculate these locational marginal carbon emissions that describe how the power generation will change as the load changes. With the power generation also, we can then compute how the carbon emissions will change. And then we solve this problem here, which is essentially a data center minimization problem where we're trying to minimize emission subject to the fact that computing loads have to be processed and different capacity constraints on the data centers. We are making an assumption here that we cannot shift in time, that all computing load has to be processed at this time, but you could also do the time extension. And then once we have solved this problem, we obtain a load profile for the data center for the next 5 minutes, and we give that into the system operator's new problem, and then we kind of move it forward like that. Okay. I will say in the beginning, we were assuming that we do this load shift and then that is a little bit more of a stylized version and not very realistic. But this is, I think, a fairly realistic way of thinking about how something like this could work. I don't know. Yeah, I haven't paused for questions yet. But yeah. Anyways, so one of the challenges that happens here is that because this is kind of a sensitivity analysis around the solution, these locational marginal carbon emissions are only really valid for small shifts. And so there can be, as we are making our shifts here, there can be a mismatch in the predicted emissions reduction and the actual emissions reduction for predicting shifting loads. And then we can get away from where goes the information about locational marginal carbon emission. You can think of that, for example, if you have a payment from a wind power plant, it would look at that node as if you have a zero locational marginal carbon emission. But if once you hit the kind of you use all the wind power, curtailed wind power, then you will have other generators kick in and provide the rest, right? So the strategy that we were trying to do here is that we use regularization, which is of course a very simple solution, where we essentially just introduce a quadratic penalty on the load shifting in the data center problem, and that essentially has the effect of incentivizing smaller shifts. And it can also be interpreted as a cost of shifting. And then essentially we have end up with a problem where we are making small shifts per time step, but then kind of they accumulate over time. So we are sort of trying to sort of slowly change the data center load rather than kind of doing more of like kind of bang type of shifting. Okay, some computational results here. So we have this RTS GMLC system, which has 5-minute data for 1 year. That is the baseline of this. We assume a standard carbon emissions rate for different generation types, and we added 4 data centers in this network with a total consumption of about 1,000 megawatts. So that's about 20% of the average system load. We assume that this total consumption is constant throughout the year, but we are allowed now. We can shift a little bit. So there's some headroom on this. The total consumption is 1,000 megawatts. I think we have about 1,200 megawatts of capacity for consuming for processing computing. Each time set. Okay, so then we will just look at the few comparisons here on different market participation and shifting metrics. I'll show you a little bit about the impact of regularization, and if you have time, we can talk a little bit about benchmarking with a bilateral model. Okay, so here are some results. So this is what I want to show you here is the then at the predicted carbon emission cost and renewable curtailment reductions. And when I say predicted, I mean what the data center believes it is going to achieve by solving this problem. So the prediction is essentially what comes out of this objective function. And then we are going to look at the actual one, which is what happens once the operator clears the market in the next time step. But let's first look at the predicted. So I have 5 different cases here. The first one is the standard DCOPS. We assume that the market is running no change. Then we have 2 cases here where the first one is a setting in which the data center offers its flexibility to the market. So it's essentially we integrate all of the whole data center minimization problem into the market so that the market knows everything about the data center and can leverage that flexibility to minimize cost. And then we have another, the other blue here is essentially where the data center solves its shifting problem, not using the locational marginal carbon emissions, but the locational marginal prices. And then we contrast, and I would say this is kind of more market-based shifting, price-based shifting. And then we have 2 other here that are more CO2-based. So one is the locational marginal CO2, and then we have this average CO2 that I was talking about, where you just sort of average out across the whole grid how much carbon emissions is there per megawatt hour. So these are the 4 different rows. In terms of the columns we are showing the tons of CO2 in the resulting across the whole year, the total generation cost, and the total renewable energy curtailment. And I think one of the first things to note is that all of these shifting reduces the carbon emissions, reduces generation costs, and reduces curtailment. But the amount of reduction is a little different. And specifically, we can see that if we leverage the locational marginal CO2 prices to locational marginal emissions to shift the data center load, we predict that we are able to reduce carbon emissions by 2.5%. Whereas for some of the other ones, it's about half of that. But we see that we get the actually largest reduction in curtailment and the largest cost reduction by shifting using the LMP. And that makes sense because one of them is focusing on CO2 and the other one is focusing on cost. But you can also see that in both cases, you also have a positive impact on generation cost in this case and on curtailment, as well as here also you get a reduction in CO2. So essentially, shifting according to the carbon signal leads to the largest reductions in CO2. And shifting according to the price signal leads to the largest cost and curtailment reductions. So that is maybe quite intuitive in a way, but it was very nice to see that this is true. And I think that the differences here is kind of why, for example, using LMPs, although maybe wind and solar tends to be lower cost than many other types of generation, that is only a partial signal of all of the CO2 emissions. Of course, this is the predicted carbon emissions. So let me show you what actually happened when we did that kind of shifting forwards in time. So we look at what happens when you're actually resolving the OPF, because this is all based on sensitivity analysis. So in this case, you can see that the actual carbon emissions, cost, and renewable curtailment reductions, they are quite a lot. They are a bit lower for this the DCOPF, building everything into the DCOPF and kind of offering flexibility to the market is the most effective way of doing this for generation cost reduction and also for curtailment reduction. That makes sense because this is kind of the best you can do really with respect to generation cost. We see that the LMP shifting achieves kind of comparable results though, which I guess is a good sign that the LMP is a good signal for shifting with respect to cost. But then we also see that the shifting according to the locational marginal carbon emissions is still the one that leads to the largest reduction in CO2 emissions. So although the reduction is smaller, almost maybe 60% of what we thought we were going to get, this is still the most effective metric because the other ones also are reduced. So essentially, cost and CO2 reductions are smaller than expected for the sensitivity-based model. So this is kind of where we then start looking at the regularization. And so essentially, this is just to show you that if I introduce a regularization parameter that puts a quadratic penalty on the load shift, see that as we are increasing it, we are reducing the amount of load shifting that we're doing by a factor of 3. So the data centers shift a lot less. The interesting thing here is that then our predicted emissions go up because, of course, we are shifting less, meaning that we are predicting that we are going to achieve smaller emissions reduction. But the actual emissions that we are reductions that we are achieving, they are actually kind of more. They actually remain pretty flat. And so what this really means is that the regularization increases accuracy, and we are getting kind of bigger emission reductions for the amount of shifting that we are doing as we are using this regularization. And you can kind of see here that how this encourages many small shifts that kind of accumulate over time. So this is sort of data center load profiles in our simulations that time they sort of move up and down. Yeah, and then we also, yeah, there's some this is very small sensitivity to the generation cost here. Okay, so that's, I think I will skip the bi-level model for now. But so I wanted just to essentially summarize here and say that, in our current environment, there is maybe a situation in which consumers can achieve better carbon emission reductions by acting on their own as compared to participating in the market. And there's a maybe there because I think there's a lot of more work that is needed here. Which metric which is being used matters a lot for the results, and I think that is kind of maybe intuitive for us as power systems people. I think it's very non-intuitive for people who are not power systems people. So all the data center people that I talk to, sometimes they are like, oh yeah, but our results look much better when we pick, the marginal versus the average versus something. And it's, of course, so I think we have a sort of, as a community, you need to help people understand this better. Because my sense is that people are going to do this regardless of everything. They are already doing it. I think that a lot of the quality of data that is out there about the load shifting is uncertain. And definitely, if you were to use this kind of marginal setting, then accounting is still an open problem. I'll get to that. Yeah, and this is just a couple of slides from our ongoing work on predicting real-time and near-future renewable energy curtailment in California. So yeah, so this is kind of part of one of our projects to try and help maybe provide some more data to help people that people can act upon to access that. Yeah, okay, so I'm kind of done here. I wanted to say we have built a really big test case for California, which we call text. So this is a synthetic grid that is based on the actual geographical locations of all the transmission lines in California. So yeah, and there's some information on here. I'm happy to talk about any of it, but I just wanted to put in a plug here. If you need a really big test case that is fairly realistic, I recommend taking a look at this, and we are also happy to talk to anyone who is interested in using it to help in that process. Okay.
Thanks a lot, Lena. I said there's already one question in the chat box, so maybe we can start with that.
Yeah.
Gregor, would you like to unmute and ask your questions, or I can read your question here?
I'm currently doing my bit in trying to save emissions, and I'm on my bike on the way to Riese, so maybe you.
I see. Yeah.
So
okay.
yeah.
Well, that's great.
So later you see you can read the question.
Yeah. Okay. So your question here, as we see it, is at which carbon price would the LMP signal bring a similar carbon reduction as the LMC? That is a really good question. We've done some analysis on that to try and understand. Essentially, if you bake if you bake CO2 price into the OPF instead. And what I would say is that I mean it depends. I mean the more you do, we haven't directly tried to compare exactly how large that price needs to be to achieve exactly the same. But obviously, as you are making that price larger, you are focusing more on reducing carbon emissions. And I would also say that that is the most effective way of going about this. I mean, this kind of trying to act on your own is kind of in a current environment, if you don't have a price, then or somehow, yeah, it's varies maybe across space and time, like, or in different parts of the world. Then this might still be interesting, but really, I mean, having some kind of systematic change is maybe is definitely better and more effective way of going about this.
Do you have some kind of knowledge?
Okay, can you please repeat the question, because
Yeah.
people online might not.
Yeah. So essentially, so your question is there inherently a difference between having a CO2 price and using and shifting based on this locational marginal emissions, right? So
Is controlling with the marginal emissions and with marginal prices? So
yeah.
Is there a structural difference between these two that we need to different?
Yes, yes. So the point is, yeah. So the difference between the marginal emissions and the marginal price is that the marginal emissions, I mean, it captures the carbon emissions of the generators, and they are not perfectly correlated with the price. So say if all generators were running on natural gas, and then, you know, you would have the most efficient generator would have maybe the lowest price of producing power, but that is not how it works. I mean, there's also a lot of sort of replacement of coal versus gas, sometimes with renewable energy, there's transmission congestion. So there is a correlation between price and carbon emissions, where lower price tend to mean lower carbon emissions, but it's not perfect. There's definitely a lot of sort of, you can have the same price and you can have a lot of different range of carbon emissions for that price. So they are different. Although when you're looking at the problem and you're deriving them, they kind of are based on the same kind of data. If that makes sense. The same kind of sensitivity data from the market outcome. Maybe as one interesting thing, I think, between the difference between having like using locational marginal emissions for shifting versus having a carbon tax is that when you're doing the marginal emissions shifting, each person and entity can sort of ask themselves, how important is it for me to reduce these emissions, and what is the premium of cost that I am willing to pay for that? Which means that you can do that individually. Each entity can make a decision about that. Say, I mean, if I can reduce my carbon emissions by that much, I'm willing to incur a cost of this. Whereas when we have a carbon tax, then that's kind of cost is set sort of for everyone, right? So there are, I think, some interesting differences there as well.
Good. We have two more questions online before maybe we can prioritize them. So it's a long question from Giacomo from KU Leuven.
Yeah.
Giacomo, would you like to unmute and ask your questions, or we can also read your questions if you want?
If you hear me, I can shoot the question.
Yeah, please.
Okay. Yeah, it's just a question about because you know, you mentioned that you get this data from CAISO about the marginal emissions. How reliable are these data for now? And what are the challenges you see? Yeah, if you needed to shift the load for gigawatt of generation, how do you treat the uncertainty in the both renewable generation and load in this case?
Yeah, so I think okay, so thank you for the question. That's a really, really good one. So when we look at CAISO, CAISO does not provide marginal emissions data, but they do provide emissions data. So you can calculate average carbon emissions from the data that they are releasing. So I think that the data on average carbon emissions across the grid are fairly accurate and possible to compute based on publicly available data. And there are, as I mentioned early on in the talk, there are data providers that provide this data. When we come to marginal emissions, it becomes a lot more blurry. So, I mean, different people and places tend to think about marginal emissions maybe slightly different ways. I mean, not always everyone uses the same kind of mathematical definition that, I mean, I think for me, it's natural because it aligns with LMPs. Other people have other ways of thinking about marginal emissions. And generally, it is much harder because it's much harder to kind of know, you know, it's harder to think about the counterfactual. What would happen if I change my load? And so so that is not publicly, that's not made publicly available. Typically, the only location I know where that is available in real time is PJM. And even PJM is acknowledging that their data quality might not be the best. And so if the transmission system operator doesn't have accurate data on that, I think it's very hard to imagine that anyone else should have that. That being said, I do think there are companies like Wattime and Electricity Maps that do a really good job in terms of trying to estimate those values. And I have a lot of respect for their methodologies and the work that they are doing to try and do that as good as possible. But of course, there's it's really hard when there is no ground truth to compare with, sort of to make sure that you are getting the right data. Yeah, I don't know if that was that your question. Was there something I missed, Giacomo?
No, yeah, that's perfect. Thanks. Maybe just one more question, just a small one. If you tried to think about the method like, I don't know, CVAR optimization or value at risk optimization in this case to, just have some kind of risk that you take into account?
We haven't done that yet. I will say, but I do think it's a very important question. So let me just go back here to this slide. So there is on the slide here. This is just we have been developing this predictor. It's essentially a classifier that says, is there any curtailed energy available or not? And as we have been doing that, we've been focusing a lot on not wanting to tell people that there is available curtailment and you should shift without actually, knowing that there is going to be curtailed energy available. Because I don't like that situation where you're telling people like, hey, there's an opportunity, but oops, we were wrong. And then maybe you have incurred a cost, maybe you end up increasing carbon emissions. So I think it's important to be kind of careful in the data that is being provided here. So we haven't really done any kind of CVAR or these kind of type of optimization around this yet, but the kind of related thinking goes into, how do we design this classifier where we are focusing on, providing, saying like, we want to be sort of sure that there is curtailment available when we say there is available. And that is important to us. So yeah.
There are 3 more questions on the chat box, but just to be fair to also people in person. So I like now to ask questions here. Lizzie, do you have questions?
Comment like oftentimes they compare the average emission factors having one location and having one system-wide. So I think it would be really interesting to have an average factor which is also locational to have that comparison between.
So that's a question.
Please repeat the question for online.
Okay, so so the question here is, typically we see that people are comparing one average carbon emissions factor for the whole grid with locational marginal emissions, but couldn't we also have a locational average emission? And I think that is a really excellent question. It comes down to some fairly fundamental things where it's not always so easy to trace electricity. Like who is actually, so once you put electricity into the grid, it goes where it needs to go. It is a little bit, and we know this from like a long history of trying to do loss allocations, which have been looking into sort of tracing electricity through the grid to try and understand, who is actually responsible for incurring losses. So there's actually a recent paper on this by some folks, Yang-Shi, Yisa Chen, and Pete Decker, who have been trying to kind of define a locational average emission. And I think they have a very interesting approach. But one of my questions there is like, really, is that really unique? What does it really mean? Like, I mean, does it really mean? I just think there are open questions, and I'm really happy that there are other people than me that are interested in trying to understand that.
Yeah.
What might be interesting also is the look at curtailment maybe, but I mean the generalizable way of that would be residual load, and then you would have you wouldn't have the 1 or 0 curtailment or not, but it would actually shift into the positive side of the curve basically. And it's we have looked at into that for Denmark, and it's almost linear, and basically how you can predict the carbon emissions?
We should talk more about about this. I will say we were trying here also to predict not only is it a zero or is there curtailment or not. We started out wanting to do regression where we are actually saying, you know, this amount of carbon emission, curtailed energy is available. We found that to be really hard. It was not we have. I mean, we are keeping working on it, but for the California data, we were struggling to get good enough results that we wanted to sort of put it out there. We wanted to be careful, but I would love to hear about your memory on that. Yeah.
We have let's get back to chat box. Actually, our colleague Doran Kelesh also is a professor in energy economics at DTU. He wrote 2 papers, but he just left because of another meeting. But since we are recording, it's good to read his question, and maybe he can listen to the video afterwards. So his first question is: have you analyzed the correlation between LMPs and marginal carbon emissions?
So we have tried to look at it. We haven't done. I would say we could have done more work on this. We have definitely kind of looked at it for different locations and different nodes, you know, in the sense that we've kind of been plotting scatter plots and trying to understand that. And there is a correlation, but it is it's not very straightforward. So yeah, it is yeah. So there's, and I think we also see that in our results that if you shift according to the LMPs, you do also achieve carbon emission reductions. But they are not as big as if you only shift according to the carbon emissions. And so that kind of tells me at least that there is a correlation, but we haven't done a deep analysis of that.
And Doran's second question is: what could be the incentive for the data center to shift based on local marginal emissions?
Yeah, I think that's a great question. So first of all, I think there is and I will just say this is based on, I mean, conversation with folks at Google who are dealing with their sustainable data center operations. You know, I think there is an interest, you know, in terms of, I mean, first of all, I think there's an interest in being shifting and have that capability in the data center operations, because of course that's a technically challenging thing to do. But then there's also I mean, I think there's this thing about like moving towards this sort of 24/7 carbon-free data center operations that they have, right? And so a little bit of that is, I guess, about being able to say, hey, we are green. I do believe that many of the employees and people who work there, probably also the executives, would like to see this happen. But also I know that the shifting that, for example, Google has been doing has helped them has had like some positive synergies with peak demand shaving. So they essentially ended up kind of both reducing cost of energy and reducing carbon emissions at the same time. So that's of course then like a win-win on all fronts, right? So I think that currently the incentive is a little bit more around like being green and developing the capability of doing this. But then, I mean, you could imagine in the future, I mean, I like carbon tracking, you know, reporting around sustainability. I think, you know, those requirements are increasing. And so then, you know, as people are starting to think more about this, that might also create incentives.
Doran, hope you got your answer. You can watch it later. We have one more question from Julian, but before that, is there one more question from here? Yes, Andrea.
Yeah, I was wondering if you have any thoughts on this being sort of an individual approach, and if some effect would sort of diminish if you have several players trying to do this prediction, and then maybe, yeah, having some more prediction errors there.
Right, definitely. I think that was
people.
Yeah. So okay. So the question is that okay. So here the question was, I mean, here we're looking at a single player making a change in the electricity market. In reality, we would have many and possibly many different actors kind of competing for the same carbon, low carbon energy. And I think that is absolutely a question that remains open, and it's not. Yeah, I mean, like, yeah, we need to study that more to understand how that would work. But at least sort of having, if we have enough people who are willing to shift to sort of low carbon energy, in real time, then that's at least a good start. So I guess like we are kind of in that beginning phase where maybe this is a starting point, and then but definitely this is a really, really good and important question that we also have been discussing, but I don't have an answer for it yet.
Julian, are you still with us?
Yes, I am. If you can hear me.
Yeah, please. Please first introduce yourself.
Yes, I'm actually working as a product specialist at Electricity Maps. So that was a very interesting presentation, Lina. Thank you very much. And that's subjects we are thinking a lot about and doing also some studies on our side. I had a question about how you calculate the emissions reduction in your results, because as you said, it's really accounting is really a problem, especially with marginal carbon emissions. So I was wondering, how you were calculating your emissions reduction in your results, and if you were using the same metric for both cases, and what metric you were using, and so on.
Thank you, Julian. Can you send me an email? I would like to talk more to you about this offline later as well. I have some questions for you. I was actually I would just say I was very hopeful that maybe I will get to meet someone from Electricity Maps somehow.
You could come again to Denmark.
Yeah, I will be here again in May. So
yeah.
Let me say so in the so I have two sets of results on my slides here. Yeah, okay, Zoom is catching up. All right, so in the predicted carbon emissions that you're seeing here, those are based on the essentially the metric that we were using in the optimization. So, for example, the marginal CO2. I'm sorry, you cannot see me pointing. The marginal CO2 here. The results here are based on the assumption that when I shift, I achieve the carbon emission reduction that the locational, that is indicated by this lambda CO2.
Yes.
So this is essentially saying like here the results in here is based on the metric that I used for shifting. And that's why I call it predictive.
Mm-hmm.
The actual carbon emissions is based on a counterfactual. So essentially what we were doing is that we ran the DCOPF for the whole year here, and we calculated the CO2 emission tons, the generation cost, the curtailment. And then we ran our experiment for the full year. And then we looked at what is the total generation cost, CO2 tons, and so on that we get after we have been running our experiment. So here we are calculating a counterfactual. And that is of course not possible in reality.
Yeah.
So I see that as a really important question here. How do we move forward? How do we actually create how do you actually allocate these carbon emission reductions, particularly if you then also have multiple actors? And this is something that we are working actively on, and I'm trying to sort of move forward on. And I would also love to discuss more with you and hear your thoughts on that.
Yeah, I think especially a thought is that usually with marginal emissions, you would have larger changes than in your average emissions, because you are really system-based when you look at average emissions. So it's also something we have thought that and noticed that you might sometimes overestimate the emissions reduction with marginal emissions, because you are specifically looking at very big changes in emissions. So that's why for the predicted carbon emission, I think it's relevant to calculate it with a metric, as you said, but then for the actual carbon emission, it becomes quite important what metric we are using for calculating it. Sorry. And then I have a second question. I don't know if I have time, Gerald.
Yeah, very short, Julian, please.
Okay, so really short. How do you see the challenge in using locational marginal pricing for the optimization when these data centers would like to maybe predict their load planning 24 hours in advance? And I think here your approach is really real time, but not really suited for forecasting maybe 24 hours in advance, or the complexity becomes much higher. So how do you see this challenge here?
No, definitely. That's a really, really good question. Of course, there's different timelines here. I mean, one thing is real time, another thing is day ahead, and another thing is like as you plan, of course. So if you stick to kind of the operational time frame of like real time, day ahead, I mean, I completely agree with you, particularly data centers who want to plan their operations ahead of time. You know, they might also need to be contracting on the market and so on. And yeah, so I think you could imagine that you are then looking at the day ahead market, that you have access to this type of information there somehow, prediction. But I mean, and maybe you could leverage a day ahead market to then try and the information from that market to do more real-time shifting, so that you actually sort of see, okay, this is the outcome of the day ahead market. You can try and already shape your load for that market. But then as you go into real time, maybe you could sort of think about, okay, what do we expect in terms of marginal emissions? But I mean, yeah, I would say I don't have any clear answers for you on that either. I think it's a very interesting and important question. And not only day ahead versus real time. I mean, there's also, particularly with the markets that we have in the US, there are many other questions, and I guess also here, you know, about who actually is responsible for a generator running. You know, I mean, there's a lot of complexity to that as well. And so I think there are really interesting questions around what are the really important things to capture in these stuff. Sorry for not being like more to the point than having more to offer there, but yeah.
Thanks a lot. I also had a lot of questions, but let's keep it maybe for lunch. Thanks a lot, Lina. Let's thank Lina. So now we could leave for the. Have you? Let me.